Hi, so I am Fabrice Desclaux, and here is Camille Mougey. We both work at CEA, in French, Commissariat à l'énergie atomique et aux énergies alternatives. I hope my English is not too crappy, and you have to understand CEA and not CIA, because it's two different things. You know, intelligence stuff, and we are nuclear stuff, so different things. So don't be afraid to talk to us after the presentation, unless you are afraid of nuclear stuff. So we are here to present you Miasm, which is a reverse engineering framework written in Python. It is born in 2007 and has been published for the first time in 2011. The code source is open source and is on this GitHub repository. It has as well a Twitter account here and a blog at miasm.re, in which you can find some of the demo we will do here, but in a more detailed way, because we won't have many time to go deep in the details. So why are we here? We are here to present you Miasm, because we only present it in the French community. So we are very glad to present you here to the international conference. So thank you, REcon. Miasm is used every day in malware researching, so malware unpacking analysis. It is used as well in vulnerability researches and firmware analysis. And we have some applied researches as well here. The first version of Miasm was very crappy, so we are doing a lot of efforts in order to clean the code base. Oh, I see someone has used the first version of Miasm here. Sorry. And there is a lot of efforts to do regression stuff and you know fuzzing and stuff like this. Okay. And today there is no real documentation, but there are documentation in the source code. And there is a lot of examples that allow us to show the usage of the API in Miasm. And keep in mind that all those examples are run during the regression test, so they are always up to date and they are working after each commit here. So as I said, there is a blog post. And we are here to show you some features of Miasm. Alors, in Miasm there are a lot of features, but we can show them in limited time, so we will only concentrate on interesting features here, and we will try to highlight them using a real case example and demonstration we will do here. In fact, we will do a live demonstration to have our shot of adrenaline during the presentation.
Okay, so the first example that I want to show you, the story starts on a friend's network when a guy browsing its favorite lolcat site ends on this page, which is actually an Angular exploit kit landing page, which detects that the browser is vulnerable, and then send this exploit, the MS lead exploit. And we finally hand on this shellcode. So the question is, what this shellcode is doing? So obviously, the first thing that you will do is disassemble it and look at it. Just to give you a taste of what the Miasm API looks like, here is a tiny disassembler in a few lines. So we start by opening the binary. Actually, using the container API, there is an abstraction of a PE11 extra. Then we instantiate a machine, which is an abstraction and a factory actually for the different architecture, and gives you the API to do things relative to the different architecture. Then we ask it to instantiate a disassembly engine, disassemble it at the entry point, get the CFG, and as it is a graph, we dump it as a .dot file. This example is in the example disassemble full, if you want to look at it. And here you have a 10-line disassembler, which is actually a multi-arch architecture for each one, which is supported by Miasm, and that support a PE11 extra. Not IDA, but well. We disassembled at the start in x86 32 bits, and we got this. Actually, trust me, there is a weird instruction, so we realized that it's encoded, and what we want to do is to emulate it. I do say emulate it because we don't want to run it on our machine, because it's by definition untrusted code. So the expected result is this. Spoiler alert. We'll run the shellcode and find that it's actually download exec payload. We get its payload from the site and then the CRUD process. So how do we do this? First, we start with jitter. The jitter is actually the way we emulate code, and here we are using LLVM, but actually we support GCC, TCC, and Pythonic one. In this jitter, the memory is emulated and the CPU is emulated. At first, the memory is completely empty, so we start by mapping the shellcode. And then as the shellcode begins with a push-pop operation, we need a stack. If we run the shellcode with this, we end on that, actually Miasm crash, but it's normal. It's the try and die approach of Miasm. Indeed, there is a kind of slider that you have in the emulation from the minimalist one to a full emulation. And the idea, here is the minimalist one, is that the segments are not supported. There is no DLL, there is no whatever. So the idea is that when Miasm will crash, it will put your finger on the interesting stuff in the binary. Here, this is this code snippet, which is a common way to get back DLL information. So we'll use now another API, which is a sandbox, which do push the slider a bit further and support segment, and we'll load different DLL, etc. To be more realistic, we will load the Internet Explorer binary and add the shellcode in the memory. So we do this, we load the different DLLs. The Windows internal structures are also built. So we had the in-memory order list information, etc. The PEB, TEB. And just a side note, in Miasm, the memory is managed at the byte level. So here the TEB is completely sparse. And we just add the pointer and the information that we know. So when a malware is doing weird or uncommon stuff, it will segfault, and we will see that it's actually doing something unusual. So when we run again on our shellcode, here the DLL is loaded, the code runs, and it ends on it crash again, try and die approach. And it ends on this error. So this error is what? Actually, when we load the DLL, we parse the export, and we said, okay, if this code wants to call this API, we break and we go back to Python, and we can use Python sub, which are just stubbing for a function. So how does it work? It's quite simple. There is just an arbitrary name, which is a convention, the DLL name and then the API name. We get the arguments. So here for Strulen, it's just the source. We then retrieve the string in Python. Actually, as it is Python strings, we can use the len of Python to calculate the name. And we get back we set the return array value, the length, and the address. And that's it. Actually, the function stub can interact with the whole Miasm emulation. So for instance, this is a malloc. We just add a new memory page. And why we are doing this? It's because we can implement minimalist API. So for instance, the URL download to cache file, we just take the URL and say, okay, it works, no problem. And the output is in the file named Toto, because we're French. So, demonstration. I launch it on this. Shellcode, the code is running, and here what we can see is that actually, I don't know if you can see here, there is several API that are being called, and you can see here the URL download to cache file on this URL, then a create process, and as we said to the malware that's actually the create process file, it tries another trick, which is to call a shell execute. And we also said that it fails, so it tries the next URL, and then we can see the every URL that every CNC that it brings with him.
There are a lot of API in Miasm that are already implemented, so cloud process, malloc, etc. So we are recoding completely Windows in Python, actually.
Now you say, okay, what doing all of this stuff? It takes maybe a bit more time than doing it with a debugger. But actually, this is a campaign. So when we got this second shellcode, which is exactly the same but with different CNC, we just reuse the same script, and then we get back the new URL and the CNC.
So the second demo is about the analysis of binary of equation drug, which is called NTEVTX64.sys. This binary is not packed, but it protects its strings, important strings in the binary. They are ciphered, in fact. And each time the binary needs one of the strings, it calls a decrypting function with 3 arguments. The first one is a pointer to the encrypted string, the second one is the length of the string, and the third one is the destination buffer. And when we are facing such a binary, we want to automatically retrieve all the strings, decrypted string in the binary. So there are 2 things to do. The first one is to retrieve for each reference of the call on the decryption function those parameters. And the second thing to do is to, for example, emulate the function with those arguments. So to do this, we have an algorithm we will explain later, which is called the dependency graph. So here is the function which is responsible of the string decryption. And here is a function that uses. So there are 3 registers as the argument. And we want to track R8 and RDX, which stores the pointer to the source string, encrypted string, and the length. So obviously, RDX is easy to recover. It's directly here. But R8 is a bit tricky. So here we see that if we do a hand analysis, it depends on this register and the offset 23. So we have to track back this register to see which is its initial value. And here we see that in this code, it is kind of set it to the value FFF, so -1. So here is the demonstration of the dependency graph. It has been coded as a plugin on IDA. So you said you need to track R8 here and here. The plugin will enlight all the lines which are implied in the computation of the register you have selected. So you have the first line here, and it highlights the initial lines, and we will explain later, but there is also a symbolic emulation, and in this case, we have resolved the value, and it says the value is 22, because 23 minus 1 is 22. Okay, so in this binary, as there are 82 references, it's a bit hard to do it by hand, so that's why we use this kind of algorithm. This algorithm is a static analysis. It allows you to do backtracking of some variables. And it's between the path-sensitive algorithm and the use-based chains. The first one, path-sensitive, is an algorithm that backtrack variables, but it will do an exhaustive research in every path execution. So, for example, if you have a loop which executes 1,000 times, it will do the research during 1,000 times for the same block. So it's a bit painful. And the use dev chains gives one full solution for a function which will be independent of every path. So it's a bit hard to to use its results. So the algorithm is a bit tricky to explain, and it will be a hard time for me. But to simplify, it will track the variable in a block, in a basic block, if this basic block creates a new dependence of the variables we are currently tracking. Okay. If you want more explanations, you have a paper here. Oh, sorry, it's in French, and a blog, and in this one it's in English. So thanks to this algorithm, we can distinguish, for example, cases like if and else. And if we have a complex loop, it will unroll the minimum amount of time the loop in order to discover all the new dependencies and give the solutions. Okay, so what's next? In the next demonstration, we will use first this algorithm on all the references of the decryption function, and then we will emulate the decryption function with those arguments, and so we will retrieve all the decrypted strings. For the moment, the only problem is that the jitter part of Miasm is a native code, so it's in 64-bit, and as you know, IDA is in 32 bits, but maybe in the near future we will be able to run a full plugin in IDA. Okay, so here is the demonstration. Let's flow the adrenaline. We run the plugin in IDA in order to do RPC calls from the out of IDA, the exterior of IDA. So here you see that we have resolved each references here, and we inject it to the emulator, and so we have the deciphered string here, and so on. And the plugin gives back the information through RPC on IDA. So you have, it's a little too, I don't know if you can do it, but you have for each call the unciphered string. Select one, Z, and we have the deciphered string here. Voilà.
So actually, in this binary, there is also a custom cryptography. In fact, they are used it for instance, big numbers manipulation. And our goal is that once we reverse once, we want to identify it everywhere, including on different architectures, because these samples are in fact in 86 bits and 32 bits and 64 bits. So actually the goal is to having a tool that is able to say in this binary framework, whatever, the function at 1, 2, 3, 4 is a mem copy or a big number copy. So as you see today, there is a state of art in these fields, but the Sibyl approach, which is a side project based on Miasm, is kind of different, because in fact when you got most of the approach are based on signatures. So for instance, the CFG or the instructions that are used. But when you faced obfuscated, for instance, here is obfuscated memcopy. Your signature that you made on the naive one is not available anymore. And moreover, if the memcopy is vectorized, here the instructions are different and the CFG. So the idea is to consider the function as a black box and do what you do when you have a debugger. You choose your input and you launch the function and you see the result. You observe the result and you compare with what you expect. So here specifically the inputs are the arguments and the initial memory. The outputs are the output value and the final memory. And we run all of this in a minimalist environment, the sandbox that you see just before, in which there is just the binary which is mapped and the stack. So just to be sure, here are an example of a few test sets. We have this black box function, and our first test is mul. So the inputs of mul are 5 and 10, and we we set the arguments, run the function, and the function crash. So obviously, this is not a mule. Then we pass to the next test, which is a strlen. So we mapped read-only strings, hello, run the function terminates with the output value 0. We compare it to the expected one, which is 5. This is not the same, so obviously this is not a strlen. And the final, it's 8 well. So the input is 1, 2, 3, 4. We run the function. We got 1, 2, 4 in int as output. This is the expected one, so this is likely 8 well. If we go back to the mule, obviously 8 well has to dereference the pointer, its first argument. So with the mule, it difference 5, so it crashes. And this is why it crashed before. So we have to have a tool that is resilient to crash, and the opposite problem, which is infinite loop. When a function waits, expect a counter, and that you give it a pointer, it will loop a very big number of time. So we just want to stop the execution. We want the test to be described in an agnostic architecture way and ABI agnostic way. And maybe one call cannot be enough. So for instance, if you use a 2 and 2 and you get 4, you don't know if it is add, a mule, po. So you have to have a test politic in which you can say test 1, and if the test 1 success, launch the second test. And of course, this is embarrassingly parallel extra. So we build a tool for it, which is named Civil, which is open source. It has a CLI and a IDA plugin. It has documentation. It's based on Miasm for the jitter, the parsing of API, ELF, and several other things. And it can be speed up using a QEMU. Actually, we are using a Unicorn, but Unicorn is actually QEMU. And it can learn a new function automatically, but this is out of the scope of today. So back to our case, we want to recognize BN copy, so big num copy. So we just have to create a class which stands for the test. Then we prepare the test. That is to say, we allocate 2 big nums, with one being read only the source, and a second one being write only the output. Then we set the argument in an ABI agnostic way. We run the function, and if the function success, we check the output, and the output is the destination is equal to the source. The test politic is naive. We just have one test. So in just a few lines, you got a test that have been written in just a few minutes, and this test will run on every supported architecture by Miasm and every supported ABI. So demonstration time. So the first demo that I want to show you is running Sibyl on BuzzyBox MIPS, because this is the kind of things that you always find on a firmware, for instance. So for instance, it found memcomp. So we'll see what it does found. And I don't see if you see it, but well, I think that you don't want to reverse this function. In addition, that you have crappy things that like the delay slot and these things. But if we use the naive jump when there is no optimization, we can see here that it does look like a memcomp. Second example is this one. Here again, you don't want to reverse it. In addition, that he is using SSF3 instruction. So we can ask Sibyl what it does things. And Sibyl say, okay, it does look like a memmove. And you can note that he's not saying it is looking like a memcopy, because actually there is a test which tests that there is the difference between memcopy and memmove, which is the overlapping gap when you're, well, okay. And to check these results, if we look at the xref, in fact, this function is being registered as a main move in SSE3. So actually, it does found the good one. And finally, if we run it on our equation test, so the first one, here I'm running it on the 32 bits binary, and it found all of this. So big number comp, big number shift, div, etc. And if I run the same test on the x64 version, you can see that just a bit slower, but he's able to find the same function at the different offsets.
So this is very useful when you analyze a binary or a firmware. And often in a firmware you have all the stuff, strulen, stocopy, etc. So you have the base, all basis functions that are named by Sibyl.
Okay, so now that we talk about emulation, there is another part of Miasm that we want to introduce to you, which is relative to the IR, the intermediate representation, and symbolic execution, etc. So to give you just a glance of what it does look like, here is a simple function. Actually, it is obfuscated, but whatever. You can ask to Miasm to translate it to its internal IR. You got this, so I just make them side by side. Okay, so there we go. And what you can see here is, for instance, actually the IR is quite intuitive. So there is just a few words in this IR, and we have it since now 10 years, and it has not been changed since. So, and we've been able to handle several architecture and all of the algorithms that we have showed to you. So we are quite happy with this IR, and we think that it will not change in the
moreover, the jitter of Miasm is based on this IR. So when you are jitting some code, the native code is translated to this code, and this code is compiled to C, and so we can emulate. This is the mechanism to emulate code on Miasm.
This is how we are actually sure that the semantic is quite correct. So, for instance, if I look at a more complicated instruction, the push, it has two side effects. This one and this one, and in fact they are done in parallel. That is to say, the ESP here and is not the same that this one. This is kind of the out and the in, like a transfer function. Okay. So, for instance, exchange between EAX and E by X is just two lines: EAX equal E by X and E by X equal EAX.
This is a bit tricky the first time you see it, because when you read that, you see, oh, there is an error in the semantic, but they are done in parallel. So,
so if I take a more complex instruction, for instance, sub, you can see that there is all of this side effect, and actually it's just the flags computation with you can see here the ternary operator, which is the same that in C for the 0 flag. The negative flag is actually taking the bit from 31 to 32, so the most significant bit. And the parity flag is computed with an arbitrary operation that we named parity, which stands for the population count in x86. But, well, there is a lot of verbosity here, so we can do compilation tricks, like dead regs and extra, common simplification. So, if I do this, I got this graph. And now it's quite simple to understand, okay? You can see that there is a lot of computation on EAX. But, well, we can do better. Actually, when you see this, the thing that you want to do is to do your math and to take the EAX here and add the different constants. So we have a big equation, and you want to propagate constant to crush it. And actually, this is just a simplification, okay? When I have 1 plus 2, I simplify it to 3, okay? Another simplification is x XOR x is just 0, or x sub x minus x is 0 again. So this is, in fact, symbolic execution. So what does it done on this sample? If I select all of this and ask to emulate it, I got this. And here what I have, the final EIP is actually the top stack. Okay, there is a memory access of 32 bits on the stack, which is the return address, obviously. And you can see that the AX have been simplified, and this is just the first argument plus the second plus lit. Okay. If I take a second example here, and I run my symbolic execution, I can hand on fun thing. Okay. Demo effect. It's coming. Okay. This. This. Okay. So if I run the symbolic execution here, what I got is that the equation of EAX is quite complicated. Okay, the second line. And in fact, there is just a simplification which is missing. If we look at the equation, we can see easily a pattern. And in fact, we have a x and a not c or a not x and c, which is repeated. This is, if you do your math, this is just XOR between x and c. So the whole equation actually here is just XOR between two arguments. So we can say to Miasm to add this simplification is just as easy as adding a new simplification. The strategy here is that we will match using a regexp in intermediate representation to match x1 and x2 or x3 and x4 because the constant can be pre-computed, so we will not see the constant and not the constants. We have to match it and then check that there are been that are actually not the one of the others. And then we will replace it with the correct, with the simplified equation. And then we'll do this for one, but we will see earlier that there are two of this, and the simplification will just propagate and will end with the correct one. So the code related to that is just, as I said before, the IR regexp, which is here. Then we check that they are equal to the not, and we replace with the correct one. We enable the bases, and what we get, what we finally obtain, is that when I run with the simplification which is enabled, I finally have EAX, which is just the first argument, XOR the second one.
Okay, thank you, Camille. The next demonstration is about analyzing this virtual machine. In a version of this, there was a function that is responsible of deciphering the CC URLs, which is compiled in a custom CPU. And so, in reality, to have the URLs, you can run the code and emulate the code and get back the URLs on x86. But if you want to analyze the code under the virtual machine, you have to reverse it. So in this demonstration, we'll show you how we do a lot of automatic analysis in order to do minimal hand analysis. So the first thing to do is, once you have found the fetch of mnemonics, we will do a symbolic execution of each mnemonic to see what are the side effects of those mnemonics. So the first one, for example, we have two equations here. So for the ones that are kind of complicated. And you have to know that the memory at ECX is a virtual machine program counter. So when you inject this information in this equation, you have this equation that gives back, in fact, that it is the update of the virtual machine program counter here. And you can deduce that the first instruction is 1 byte long because it adds 1. The second one is more complicated. Here we have the virtual machine program counter, and we can see that the byte at the virtual machine program counter +1 is updated using XOR with strange constants and the current bytecode of the current mnemonic. So here, when you have done the symbolic execution, you may have some expression like that, and the idea here is to apply reduction rules to automatically get the high level of semantic of the instruction. So to have those reduction rules, you have to do manual analysis. So you have to know that, for example, ECX is a pointer to the VM structures, which stores all the registers of the virtual machines. So here we have less than 10 reduction rules. This one is, for example, ECX is a pointer to the VM struct. So the deref of VM struct will give the virtual machine program counter, and something like the deref of the VM structure plus an integer is the register X. We don't know the number of the register, and so on. An integer will be reduced as a generic integer, and something like this. So a lookup at virtual machine program counter plus an int will give an int because it's obviously a lookup of the immediate part of the instruction, which can be used for the offset or for the register number, for example. And the last one is that we have any operation between two integers will be reduced as an integer. So if we go back to the final equation given by the symbolic execution, we will do this first algorithm in order to apply reduction rules. So we can apply first on those leaves ECX, and we will apply it, and it will give that ECX becomes the VM structures pointer. So we will replace all those leaves which are integers by the generic integer token here. So now we can see that here we have a reduction rule as well in red. And this one is a reduction in order which will give the register X. We don't know for the moment which exactly is the number of the register number. Here in red, we have a lookup of the VMPC register. So we have another lookup here, which will result in the fetch of the immediate part of the instruction. So it is reduced, as an integer. And here we have an operation between two integers. So this is an integer. And we end with this expression, and there is no more reduction rules that can apply. So we stop here, and here we have a simple addition between a register of the virtual machine and an integer. Okay. Those reduction rules can be seen as reduction rules like, in Lex and YAC stuffs. So when we execute, when we do a symbolic execution on every mnemonics, and we apply those reduction rules, we obtain those equations, and it's a bit simpler to see this, to see which mnemonic correspond to which semantic. So here, for example, we have a simple XOR between a register and an integer, and we have the update of the virtual machine program counter. In this one, we have a write to the memory, which will in fact is a XOR with a simple integer, and we have an update of this register. So in fact, this instruction is a kind of, addition in memory with a post-incremental pointer, like for example on ARM architectures. And this one is the same one, but in 16-bit. But we can do more than this. So for the moment, we only reverse some structure of the VM, and we let Miasm return us the intermediate language of every mnemonics. And now we want the native code of the original binary. So what we will going to do is to apply those equations and to instantiate them using the bytecode of the VM, so we can resolve the regx and look up its register number, and so we have automatically the disassembling of the virtual machine without writing any disassemble code here. but we can do better.
So actually, what we got looks like something like this. And this is the full disassembly of the VM. So I do know that you can see a lot of things, but here we have not just a trace. Okay, we have the full control flow.
If you zoom a bit, you can see that even this code is obfuscated. See the addition here. So it's still obfuscated.
Okay, so actually this is Miasm IR, but we can do more than that. In fact, what we can do is translate this to LLVM IR, which leads something like this, and then we can compile it to x86 again, and to obtain the code, codes which look like this. So the demo, it's quite easy to do. I launch it. Okay, it translates to LLVM IR. Then I obtain something which look like this. Come on. This is complete with optimization options, so the obfuscation that we just see is actually reduced. And we finally end with this tiny code, which is much simpler to understand. You can also see that there is custom operation. There are calls to RC4 that we detect in the mnemonic analysis.
In fact, there are very quite complex mnemonic in the virtual machine. For example, one mnemonic is a full decryption with its key embedded in the mnemonic encoding. So you have mnemonic of about 20 bytes or 50 bytes long.
And that we can do more than that. In fact, what we can do is re-inject this code in the original sample. And if we do so, we obtain a quicker malware sample. So we optimize the malware. And when we run it, actually we instrumented the RC4, so we can see that there is some calls. And we dump at the end the error that have been deciphered. We see that this kind of configuration and the code works well, and we end with the CNC output. Another thing that we want to show you is if you remember the first shellcode that we analyzed, you have seen that obviously the shellcode is kind of packed to be alphanumeric. Okay, we can see here the URL. So the idea is that actually this is a campaign which is associated with Angler exploit kit, but can we steal the packer from this shellcode? And can we do it in an automatic way without actually reversing the associated stub of the packer? And moreover, can we make our own download exec payload with a REcon URL? And the response is yes. So how we do this? We use which is called dynamic symbolic execution or concolic execution. This is not something we invent. The principle is quite easy. Actually, there is just a symbolic execution which runs alongside a concrete one. Okay, and the concrete one helps the symbolic execution to deal with loops and external API. So, for instance, if I take this small code snippet, there is just a branch on X, which is unknown. But during the concrete execution, of course, X is set to a constant. So, for instance, it entered the if. If we do a symbolic only execution, the execution will get stuck on the if, because you don't know if we have or not to take the branch. But using the DSE, in fact, the concrete execution will tell it that it does take the branch, and then the symbolic will say, okay, I take the branch, so I do know that X is odd. And I continue in the branch, in symbolic, okay? If we apply this to our shellcode, the idea is that I will just init the DAC engine. We attach to our G2 that we see before. We, for the moment, concretize all of the symbols in the symbolic execution, so all is concrete. And then we symbolize the memory which corresponds to the shellcode bytes. So the P, Y, E, E, I that you see before is now symbolic, but the stack, etc. are completely concrete. And we add the breakpoints at the original entry point. We then if we run and break on the original entry point, what we can do, for instance, it dump the equation of the resulting memory bytes. So if we do this on TIS1, what we can say is that it's actually a stub which is pretty simple. It does XOR two memory area, and one of them is nulled before. So the whole idea is, the plan is to force the final memory to contain our URL, then to force the initial shellcode to be alphanumeric, okay? And we'll ask a solver, so here it is Z3, to rebuild the new shellcode, assuming the different path constraints which are enforced by the packers, and the final memory equation that we get. And this way we can steal the shellcode. So, demo. So the code is quite simple, okay? So it's just a few lines. If I launch it, so the first thing that it is doing is to instrument the code until it reaches the original entry point. It should work. Come on. And once it will reach the original entry point, it will modelize the equation, ask the solver, and then get a solution, which is here, okay? And if I look at this one, you can see that it does look like what we have before. But you don't have to trust me. If I run the previous script that we wrote in the first section on this new shellcode, what we got is that the script is now, this payload is now downloading from recon.cx/payload and create a process from it.
Okay. The last demo is to show another engine in Miasm. The first one we showed that was the symbolic execution, and there is a second one, and which is the minimalistic. It's an engine in which we will propagate C types. So we are using to do type propagation. We need two things. We need structures and types. And so you can have them if you, for example, reverse a binary, an EFI binary, because structures are open, or if you have already reversed a binary and you have recovered its structure, or for example, you have a vtable recovered by some tools. And the second input needed is the packing of the structure. For example, if the structure is packed or aligned on x86 or 64-bit. And when you give this to this engine in Miasm, Miasm can answer simple questions. For example, if you say that RX is type is struct foo, you can ask Miasm what is the type of RX plus 8. So it will obviously give here star. And if you ask the type of this equation here, it will answer this type. So now that we have this basic stuff, sorry, we can inject it in an engine that will do fixed point research and so propagate type in a binary. I won't explain the algorithm because I think we don't have many time. So here is the demonstration. So here we have a binary which is a model EFI of this computer, I think. So we know that the second argument here is a EFI system table star, and we get a file, a C header file, which is named BMOS, which is a pre-processed header file which contains every structures of the EFI. We didn't write any C parser. We use a tool called PC parser, which is a Python module. So we give first this C header, And we give as well the fact that it's for AMD64, so now Miasm knows the packing of those circuits. And we will give as well the hint that EDX is of type EFE system table star. And now we will run this on the entry, main entry of the program. And here it will auto-comment that, okay, this one I give him, so he knows that RDX obviously is EFE system table star. So he knows that RBX has the same type, but here he knows that at this point, he knows that this memory memory is of type EFE boot service star. So RX is of the same type, and here the call, it is resolved, and we can see that this is resolved to a function pointer that is called EFE create event, which has those arguments, and so on here for the other calls. With this plugin, you can as well give, you know, in EFE, often the binary gets the EFE system table and store it in a global variable, so it will have it for the whole binary. So this is another example in which we will run again the plugin with those information. We reverse it, and we know that those globals, and we know their types. So we run it on a bigger function here. And we can see now that here we have a call to the function which type is EFE input read key. And we see next that we have a variable which compared against y and y. So we can see that it may match the code here.
Okay, this is an example of type propagation, but there is other domains that we are working on. For instance, intervals of value and tainting. But we don't do for now automatic type recovery or backward propagation, but we are still working on. So to sum up, we covered several samples from sandboxing of malware to IR and symbolic execution. I hope that at least one of the samples talk to you, and that the next time you will consider using Miasm for your problems for fun and profit. And unfortunately, we didn't have time to talk about how it works under the hood, but the support is free, as in free beer. So don't hesitate to come to us, especially with the beer. So I hope you enjoyed this talk, and thank you. I don't know if we have time for questions.
Il y a une question là. Ah non. Ah.
Hey, I was just wondering what architectures you support.
Okay, it was on the first slide, but we just go very quick on it. Okay.
Currently, it's x86, 32, and 64-bit. It's ARM thumb. We don't support every ARM thumb 2 instruction at the semantic level. We have MSP 430 for the the micro corruption challenge.
R0.
And
we
ARM 64-bit.
Yep.
And SH4.
And there is a PowerPC that is on its way.
In current.
Thank you again.